All right, welcome back everybody. So we are ready to continue, and we are continuing listening talks about hetero complexes and multi-polynuclear complexes. And our next talk will be given by Professor Marius Andruh from the University of Bucharest. Yeah, we already can see your slides, so please go ahead.
Hello from Bucharest. I am very happy to attend for the third time this conference, and I would like to thank Professor Ovcharenko, Drs. Fedin and Weber for inviting me and for the excellent organization of this very interesting and useful conference. So we are interested especially in designing complexes containing different spin carriers, with a special emphasis on complexes containing 3 different spin carriers. This can be either 3 different metal ions or 2 different metal ions, and the third one, a paramagnetic organic ligand. So there are, as you know, there are many families of radicals, and we have selected the nitronyl nitroxide family simply because these molecules can easily act as ligands towards both 3D and 4F metal ions. They are quite versatile because they can connect to one metal ion, they can act as diatomic bridges or monoatomic bridges, they can connect 2 different or 2 identical metal ions. So since we have passion for orthovanillin, that is a very accessible and useful starting material for designing new ligands, we decided to employ it as a source for radicals. And the only information existing in literature, the one indicated here in red, gives an idea about the existence of this molecule that was never employed as a ligand. Moreover, the yield is very low. So in order to improve the yield, we blocked the para position with respect to OH group, and we were able to obtain good yields this radical that was employed by Professor Ovcharenko in his group for the first time in 2017 in designing some cobalt complexes, and the synthetic procedure was reported in 2004. So this ligand is quite simple, and it can be interesting to synthesize compounds with both 3D or 4F metal ions. Let's start with the complexes containing 3D metal ions. So all these species are mononuclear. So it's nothing special concerning the structure of these compounds, but they are very useful models for magnetostructural correlations and for other complementary techniques, for example, IPR. So first of all, in some cases, it is interesting to record the UV visible spectra just for a better characterization, like in the case of the nickel complex here, because generally the strong absorption bands of the radical obscure the DD transitions. But in some cases, like this one, we can observe the signature of an octahedral nickel ion. This is the first DD transition of nickel 2. So what about the magnetic properties? So the exchange interaction is quite strong. So the metal ions are coupled even at room temperature. And the most interesting feature to be observed is that we have a large plateau here that indicates that we have only this ground state, S1/2 for the nickel complex and S = 2 for the manganese complex. So the fitting of the experimental data leads to the following values of the exchange parameters. So this data can be theoretically rationalized by DFT calculations, and we found the theoretical values close to the experimental ones. So because we have this plateau I mentioned before, it can be interesting to investigate the EPR spectra with a final aim to detect whether or not our compounds can be used as qubits. So first of all, the zinc radical derivative, since zinc is diamagnetic, we will observe on all the temperature range only the signature of the radical. And we also can observe that the local symmetry for this radical is rhombic. So the measurements have been done both in X and Q band. More interesting for us is the nickel derivative. The nickel derivative because we can observe below 120 Kelvin, the signature of S equal 1/2. So this is these are the spectra recorded in solution or frozen solution and in powder. And we observe the signature of the radical at room temperature and at low temperature, both in powder and in frozen solution, we observe the signature of the S equal 1/2 ground state. By decreasing the temperature in both X and Q bands, we observe the rhombic symmetry of the resulting ground state through the antiferromagnetic interaction between nickel and the radical. The case of manganese is even more interesting because we can observe below 120 Kelvin nice spectra of S equal 2. So this is in X band powder, this one, the other one in Q band, and the simulation of the spectra is in both cases, the simulations are in line with the experimental lines which are observed. We also checked the ability of this ligand to generate 2p4f complexes. And since we observe a degradation of the hexafluoroacetylacetonator ligand during the synthesis, resulting in, this is a well-known situation, resulting in trifluoroacetate ligands. We checked the purity of the crystalline phases by powder X-ray diffraction, just to be sure that even we observe this decomposition of the ligand, we have pure crystalline compounds. So the magnetic properties and the spectral properties have been investigated. The spectral properties, especially for dysprosium, just to emphasize the FF transitions, which are presented here. And on the right, the magnetic properties are displayed for gadolinium, terbium, and dysprosium. For the gadolinium compound, you observe an overall antiferromagnetic interaction, while for terbium, we observe at low temperature a slow increase of the Kaiti product. So the treatment of the data together with the ab initio calculations are in progress, so I will not insist much on these compounds, just mentioning that unfortunately for the terbium and dysprosium derivatives, we do not observe the slow relaxation of the magnetization. So the final aim of our work is to design systems containing 2p, 3d, and 4f spin carriers simultaneously. So this is simply because from the synthetic point of view it's challenging. It is not so easy to put together in one pot reactions two different metal ions and a radical. So most of these syntheses reported in literature, including ours, are rather serendipitously cases, because we do not have any, it is difficult to control the nuclearity of resulting clusters or the dimensionality of the coordination polymers, or whether we can obtain discrete species or coordination polymers. Anyway, all these compounds are interesting and deserve to be investigated. So we designed a rational synthetic approach towards such systems. And this is based on our former experience in employing compartmental ligands. So I already presented this part 3 years ago in Astrakhan, so I will not insist very much on all the data which are already published. But I only want to mention this strategy allows to obtain strictly binuclear compounds because we have 2 different compartments, each compartment able to accommodate one type of metal ion, or 4D and 3D. So unfortunately, the resulting topology is linear. And also the beauty of the synthesis has been illustrated from the magnetic point of view. It was a disaster because the 2p4f, so containing only 2 spin carriers, the 2p4f system was a single molecule magnet, while the 3-spin system was not. So the next important step in our chemistry is to force the 3 spin carriers to work together. In other words, we are looking for synergistic effects between these 3 exchange pathways. And this is possible only having this topology. And in order to reach this topology, we removed one of the nitrogen atoms from the Mannich arm here. This is a Mannich fragment. And the absence of this nitrogen atom will eventually force the nitroxyl group to act as a bridge between the 2 metal ions. And indeed, it was successful. We have the first examples here of systems where the aminoxyl group connects 2 different metal ions. So the procedure is general, irrespective of the nature of the lanthanide or of the 3D metal ion, cobalt, manganese, nickel, and so on. And the strategy works, and this was published 2 years ago. And indeed, the 3 spin carriers work together, and this leads to a single molecule magnet with a quite high blocking temperature. All this data have been analyzed by us recently and compared, and this is our case, this is our first case, and this is other sequences of the spin carriers which have been observed in literature. And the main result of our work is the fact that the quite strong anti-ferromagnetic interaction between the 3D, in our case cobalt, and the radical will have a strong influence on the energy of the Kramers levels of dysprosium. And this shows for the first time that we can force the 3 spin carriers to work together in order to improve the magnetic properties. So back to serendipity. We employed the ligand I discussed before in a one-pot reaction with a 3D and a 4F metal ion. And we obtained a 3-nuclear compound, and again with this triangular topology. So for the moment, I present here only the structure of this new example of system containing 2 aminoxyl groups acting as bridges between two different metal ions. So actually, we doubled our first triangle we reported before. So the second ligand was synthesized by my PhD student Mihai Răducă, the first one by Cristian Spânu. And this starts from a well-known precursor in designing, again, compartmental ligands. So the controlled oxidation of this dialcohol leads to the monoaldehyde. This can be separated by chromatography. And then following the classical synthetic Ullmann's procedure, we obtain this ligand that has to be blue, and the immunonitroxide that generally is red. So we were, especially my PhD student was intrigued by the color of the system, because although he separated a blue component in solution, the crystals were red. And that prompted us to investigate the crystal structure. And this is a quite strange case, because the two NO groups are no more coplanar like in all the nitronil nitroxide ligands reported before. So we have this planar triangular moiety that is quite normal for such ligands, and this nitrogen atom shows a square pyramidal geometry. This one, and then we look carefully whether we have a correct crystal structure, and the occupation factor of this oxygen atom is quite high. So that means that we have the nitronile nitroxide ligands plus an immunonitroxide. Anyway, the distance between this nitrogen atom and the oxygen atom here is longer than the other NO bond. And in order to be sure that this is general for our synthesis, we have recorded 10 stricter, we have measured 10 stricter crystal structures from different syntheses, and the crystals, with two exceptions, are very good. And we are pretty sure that in our compound, the two NO groups that leads to this delocalization are no more coplanar. And using this paper coming from Professor Ovcharenko's group, we have compared all the distances, and in our case, this one is longer than the one that is characteristic for the aminoxyl group in the nitronil nitroxide ligands. So the crystals are red, while in solution, the system is blue. By isolating the crystals from the solution, we go back to the red crystals. And this was an interesting case to be followed by UV visible measurements. And indeed, for the crystals, by diffuse reflectance technique, we recorded this spectrum with this band around 800 nanometer. And this band disappears in solution, and we have a blue solution. In order to identify the origin of this band, we carried out DFT calculations for the molecule with the one we observed in the crystal structure. I mean, the one with the oxygen above the plane of the molecule. And we observed a transition around 800 nanometers, this one here, that disappears by diluting the solution. So these three spectra were recorded in different times. First, in the first step, we observe this. This is the same solution. We observe this band, and in time, this band disappears, but we still have this band here. So these are transitions for between the HOMO and LUMO orbitals in the molecule in the crystal, while this one is the so-called optimized. I mean the one with the 2 nitronil nitroxide coplanar, and for sure this is the species we have in solution. And because we have this occupation factor and the remaining molecules are immunonitroxide, we simulated the spectrum and we found this bound that is still present in crystal phase. This compound crystallizes in a non-centrosymmetric space group, and the explanation is the fact that this nitrogen atom is chiral and this oxygen atom is involved in a quite strong hydrogen bond interaction, but I'm not sure that this is the origin of this strange geometry, because we have other hydrogen bonds involved in this NO group. It's true, a bit longer, and the fact that the molecule crystallizes in a non-central symmetric group means that we have to analyze carefully what happens in the crystal. And we identified indeed supramolecular helicoidal chains. And to be more visible, we simplified this perspective view with this one by removing carbon atoms. And now the formation of the supramolecular helicoidal chains is clearly shown in this picture. So the origin of this crystal packing is the fact that we have this nitrogen atom frozen in a chiral configuration here. So we have our ligand. Now we can proceed to synthesize the complexes. And to our surprise, we obtain a mixture of complexes. So with the imino, this ligand here, the desired ligand here, and some traces of the starting material. So this is not good when we are interested in investigating the magnetic properties, so we have to do something. And my PhD student succeeded to optimize the synthesis, and working in the presence of 3-ethylamine, he succeeded to obtain the pure compound. And by adding an excess of 3-ethylamine, it is obtained another compound, this one here. But this is fully uninteresting for us. We are interested only in this compound. And to be sure that the crystalline phase is pure, and together with the elemental chemical analysis, we are now sure that we have the desired compound. The desired compound that is binuclear, and the 2 lanthanides ion are connected by a phenoxido group. The nitronyl nitroxide moiety acts as a monodentate ligand towards each lanthanide ion. And in these structures, the 2 NO groups are coplanar. So the oxygen atom is out of the pentaatomic ring only in the crystal structure of the ligand. So I will present only the preliminary magnetic measurements for the 3 compounds. So gadolinium, and so in this case, we observe an overall ferromagnetic interaction, the terbium derivative and the dysprasium derivative, and our measurements indicate that unfortunately this compound is not a single molecule magnet. But the final aim of our work using all these ligands is, as I already mentioned, the synthesis of the hetero-trispin complexes. So I would like to thank again my co-workers, Mihai Răducă and Cristian Spunu, who both are in the virtual audience now. Andrei Pătrașcu, he synthesized the Hetero-Trispin complexes with triangular topology. Sergiu Calancea was a postdoc in my group, and he worked together with us on the design of the new paramagnetic radicals. Teodora Mocanu solved the crystal structures. Professor Mihaela Hillebrand did all the DFT calculations. The magnetic measurements were done by Jean-Pascal Suter from Université de Toulouse, and my former PhD student and Daniel Martins, Floriana Zune and Daniel Martins from Manchester for the EPR measurements, as well as Gabriela Ioniță for part of the EPR measurements. So thank you very much for your kind attention, and once again for the invitation to attend this meeting.
Thank you. We're perfectly on time, and we have time for some questions. Виктор Иванович?
Слышно меня?
Yep.
Marius, thank you very much for your so interesting presentations. Your very complicated molecules contain potentially many functional possibilities. Such compounds very often exhibit oxidative activity towards various organic substrates. My question is so, did you register any oxidative activity of your compounds towards any substrates?
No, we didn't observe any redox reactions with our radicals. So we already synthesized a quite large number of such compounds. So the only case we observed is the transformation that you know very well, the one between nitronile nitroxide and imino nitroxide.
Okay, yes. It's one of them. And another question, if possible, you know, sometimes polynuclear compounds contain a lot of hexafluoroacetate, coordinated hexafluoroacetate. Did you check for some of them possibility to sublimate?
No, we didn't try because we were afraid for the decomposition of the organic of the entire framework. So we didn't try, but this can be an interesting idea because at least two families I presented today, they contain trifluoroacetylacetonate and of course HVAC ligands.
It's every time a balance between stability and possibility to sublimate. Thank you, Marius. Thank you.
Thank you. Do we have any more questions? I can't see any. Okay, so thank you again, and we are ready to proceed further. And we're going back to Poland, again to Jagiellonian University, and our next speaker is Robert Podgajny. And I can see you, so take it away.
Yes, I'm ready. Just let me share with you my screen. Was it? Oh, sorry.
So for now, we see your desktop.
Okay.
Yeah, now it's okay.
Now it's okay. Sorry for this delay. So this is the title of my presentation. I come from Jagiellonian University from Krakow, and today I would like to say something about the Trimetallic Cyanido-Bridged clusters. Speaking about cyanido, firstly, I would like to also thank the organizing committee, especially the Professor Fedin, for inviting me to be among such noble scientists from Russia, Japan, Germany, and other countries. Thank you very much. Speaking cyanides, we think about two phenomena, which are firstly charge transfer or electron transfer, which occurs very nicely through the Cyanido-Bridged linkage, and also exchange interaction, which allows us to connect spins to act and to be described together. to produce ferromagnetic or antiferromagnetic exchange interactions. This also can be combined with the different strategy towards different topologies and dimensionality, going from zero-dimensional molecules through chains and layers. We can reach three-dimensional networks, and this could produce us the very nice magnetism-based functionalities like long-range magnetic ordering with magnetic anisotropy, single chain and single molecule magnets, also spin crossover and charge transfer induced spin transition, and also the magnetocaloric effect. Today, I am going to focus mostly on the zero-dimensional compounds and spin crossover, generally understood spin crossover properties. But there is another issue which should be considered, in my opinion, and this strategy was indicated during this conference for several times, especially for today, that we can use the cyanide-based networks or clusters or architectures OB, so-called molecular modularity. That means that we can obtain repeatable backbones of network with exchangeable occupation of the metal ion sites, exchangeable occupation of ligand sites, possible fragmentation or structure opening, and going after this modified properties. Also, this here we have some archetypal types of chemical architectures which are the best to show this modularity. Of course, this is not all. Coming to the discrete shapes produced by polycyanido-metalates, we can distinguish over the dozen of forms, starting from the square, through circles, through fused square, to the cluster-like shapes, starting from trigonal bipyramid, octahedron, cube, and finishing with something which is the most familiar to me during last year, six-cup body centers cube. Several authors shown a very nice repeatability and possibility of introduce different metal ion combinations in the squares, trigonal bipyramid, octahedrons, and today I will speak about what I did what we did with my coworkers during several last years for this one topology. For those who are not familiar with this topology, it can be formed by octacyanometalate complexes and 3D or 4D metal ions to produce concentric octahedron, which is formed by 3D or 4D metal ions, the valent one, and this is octahedron, of course, and this is cube. This octahedron, which is made of octacyanometalates. And when we take the look at the coordination details, here we have fats, 3-cyano, 3 alcoholic units, 8 of them. Here we have 6 octacyanometalates, and in the middle, the most interesting one, bivalent metal ions, which are surrounded in almost perfect octahedral geometry by 6 isocyanides, of course, coming from bridges, from the Cyanido-Bridges, of the possibility opportunity I described at the beginning. And of course, such super complexes may be the coordination chemistry can be performed as we did it with the single ion complexes. It is due to these external sites which can be substituted where ligands, the original one, can be substituted. And these are some examples which I used in my previous research. Yes, a year ago, I had the pleasure to review the things which I have done. I'm going to show you soon what can be done with such cluster. And I divided it into 2 points. And today I would focus mostly on this one. The point is that in such a rich coordination polynuclear core, we can play with different composition, and we can do it in the way which goes as a molecular solid solution, or maybe something like scrubbing, or with site selective occupation, where specific metal ion site, due to its properties, can have its own positions. So now let's focus on that one. Depending on the composition of the cluster, we can go through the bimetallic cluster, in example, iron tungsten, iron rhenium, and trimetallic composition. This cluster can undergo reversible phase transition, which can be coupled with the electron transfer, intermetallic electron transfer, which is governed by temperature, as well spin crossover, and also trimetallic composition can host such properties with the more sophisticated and complicated manner. And here, this magnetic curves is just to exemplify that in each of such composition we can have phase transition, but they have very different characteristics. That is, that they are based on various processes. So, starting from this trimetallic composition, I would like to present you the first trimetallic composition based on cobalt and iron, which can be exchangeably put into the external and central position, and 6 tungsten ions. The composition of these phases and compositions of clusters are governed strongly by the composition in solutions, whereas grown. So this is iron-rich part and cobalt-rich part. These are crystals which grows from this solution. And starting with powder X-ray diffractions and DSC data, we can see that we can phase transition with the thermal characteristics, which are composition dependent. Also, the type of transition, I mean the first type or the second order of transition, can be observed depending on the composition. In example, for iron-rich complexes, we have quite sharp transitions, which can be seen also here. But when we increase the amount of iron and increase amount of cobalt and decrease amount of iron, the transitions becomes less steep and finally vanish. So these are magnetic spectra, magnetic moment characteristics for the whole series. Here is the cobalt limit, this is the iron limit. And for cobalt-rich complexes, we do not see the phase transitions. That means that we have the stable composition composed of high-spin configurations of cobalt-2, iron-2, and iron-5, which gives us high-spin clusters with quite notable magnetic moment and slow magnetic relaxations with parameters drawn here. Okay, these barriers are not that big one, and I must say that they are also obtained with some degree of confidence, but they are here present. What is more interesting in this network is this part, the part of phase transition which have clusters rich with iron. So, what kind of processes should we consider to describe such the change of magnetic moment? It's not very big, but it is consequently systematically changing, going from higher temperature to lower temperature and finally vanishing in this region. So these are electron transfer composed with spin crossover on cobalt and simple spin crossover of iron. We did not consider here the pure cobalt spin crossover for some reasons. So how to get the information on what's going on in these phases? We performed for each compound in the series, we performed the temperature-dependent IR spectroscopy and Mesbauer spectroscopy, and these are illustrative presentation for this iron-rich phases. We clearly see the change of the characteristic, showing us change between tungsten 5, so 1 unpaired electron, and tungsten 4 in low temperature with 2 paired electrons, so no magnetic moment from tungsten. Also, the Mesbauer spectra show us clearly that here we have a domination of electron electron transfer between iron to high spin in high temperature and iron free high spin in low temperature. But the most important informations can be drawn from the temperature variable structural data. So now let's focus on cobalt-rich phases. So where no transition is observed, these are valence electronic structure, and looking at the distances between 3D metal ion and nitrogen or oxygen, we see that indeed here we have the clear situation where these numbers 2.10 shows us that there is no transition. But when we go to the iron-rich complexes, we have distinguishment of the bond lengths in central position and in the external position. And basing on this data, we assigned that in the central part, most probably cobalt-2 is located, which changes from high temperature to low temperature into the low spin cobalt-3. In the external position, we have the domination of high spin cobalt-2, iron-2, and iron-3 in low temperature, such a spin state. And this is the change of the spin state according to this data. There was a question still, and the question is still valid in my mind. Every time I'm thinking about it and showing this data, I'm not exactly sure if we do not have some signature of iron-2 in crossover. So let's compare again the magnetic data for the cobalt iron tungsten with phase transition with the one with pure iron tungsten when there is no spin crossover, okay, at this region. Yes, but looking at the magnetic curve, we note that here there is something which looks a bit like preliminary spin crossover. But according to our current understanding, this spin crossover is not complete over the network. So for each two cluster, only one spin crossover is located here. Then this spin crossover induce somehow the electron transfer behavior, and this is the way we understand it. All this is in agreement also with the structural data shown here in low temperature. So here we have domination of iron-3 high spin and cobalt-2 high spin, and here we have the in high temperature domination of iron-2 and cobalt-2. We can also, we use the temperature variable IR spectroscopy and Mesbauer spectroscopy to show the changes in this compound. They are a bit different compared to the trimetallic ones with phase transition. Okay, so for this moment, I can say the problem is unsolved. Yes, because about the occupancy at the central site, we can say that cobalt could prevail over iron because smaller ions with larger ligand field stabilization energy locals preferentially at emitting sites and one site. I will show it soon. Also, we noted that introduction of cobalt-2 stops initial spin crossover at iron-2 and also destabilize the low temperature phase, which is obtained after the electron transfer. Although we still have some problem in distinguishing of some of the valence and spin state of interest by the techniques. The final answer could be provided probably by anomalous X-ray scattering for this moment, I do not have force to apply for this, but maybe in future I will do this. Now let me focus your attention on another series. Here we performed the similar studies for iron tungsten rhenium mixtures. So now we played not with metal ions, not in this position, but in this position. And here are the magnetic data, Chi-T product over T. And from this comparison, we clearly see that in most of phases, we observe the spin crossover, but with the high temperature, but with low temperature phase, low temperature phase stabilization, depending on the amount of iron and depending on the rhenium and tungsten. Yes, and here are the structural data, iron nitrogen and iron oxygen bond lengths, which are in agreement with the spin crossover in rhenium-rich phases. And only in the tungsten limit, we have something which looks like a combination of preliminary spin crossover with the electron transfer between iron and tungsten. This was also confirmed by the IR spectroscopy, which show the hump, which is characteristic definitely for tungsten 4 in tungsten-rich phases. So here we have electron transfer, here we have spin crossover. So this definitely shows the difference. Okay, this we can skip. Another series is the series where we mix iron 2 and manganese 2 in these green sites. And again, we have two regions. In manganese-rich phases, we have something which looks like spin crossover, and iron-rich phases, we have definitely something which looks like electron transfer. And moreover, the position of the transition is shifted towards lower temperature, yes, with the decreased amount of iron. So this is somehow consistent with the data which I shown you before. So this material is now under preparation. Comparing the magnetic data with structural data, we can see. I would like to draw your attention to the central part in 100K. In the iron-rich phases. So here we have iron-free. And these are the bond lengths which are characteristic definitely for iron-free in these clusters. But here we have a sudden drop, and in the manganese-rich phases, so here we have something which looks like iron-2 low spin, which supports our suggestion that here we have spin crossover and here we have electron transfer. Again, with IR data, we are able to confirm this data. The main conclusion from this composed research is that in iron manganese tungsten phases, we have definitely a high temperature phase stabilization. So this is this curve. This is the curve which is compared with bimetallic iron rhenium phase. Going to the iron rhenium tungsten trimetallic phases, we have the stabilization of low temperature, low phase stabilization, which can be related to the statistically shorter MN distances and generally smaller cluster size compared to this series. Okay, and now we come to the series which has no phase transition, nickel, cobalt, tungsten, and manganese, cobalt, tungsten. What is the most important outcome of this research is that we have the preference of occupation of the central site with the metal ion with smaller distance, with smaller bond length, due to ligand field preparation, ligand field stabilization energy. We know that for nickel, this term should be the largest one. So when we put in the solution, we put even small amount of nickel, in the crystal data, we see that this metal ion is located here. This is based on the data for bimetallic, nickel tungsten, cobalt tungsten, and manganese tungsten. Again, in the manganese cobalt series, we see the preferential occupation of the central site with the smaller metal ion. With the external side, we have rather the statistical occupation according to the composition of solution. Yes, here we were able to shape the high spin in the ground state, basing on the cooperation of ferromagnetic interaction between cobalt and tungsten and cobalt and nickel, also known from the literature. While in another series, there is a competition between ferromagnetic interaction between cobalt and tungsten and anti-ferromagnetic interaction between tungsten and manganese. And this is the whole series. And using the Phi software, we are able to shed the light on possible changes depending on trimetallic composition along the smaller model, because of course of the computational time and ease. We in some compositions we also obtained the moderate barriers for slow magnetic relaxation, and the data are shown here. Okay. And coming back very quickly, because I'm short of time, for the external functionalization, we can do it by capping ligands, by increase of nuclearity, and the formation of cluster-based coordination polymers. Using this approach, we obtained quite a lot interesting topology. For the most important issue is here that with cobalt tungsten cluster and such ligands, we obtained the network where two clusters are shown, one with 6 ligands around and one with 7 ligands around. This is in the opposition to the other ligands where we have the 8 coordination. And only for this one, we have also notable slow magnetic relaxation with delta, with the barrier of about 30 K, quite similarly to the original bimetallic cobalt tungsten clusters. We observed also some field-induced slow magnetic relaxation on tungsten manganese cluster, which are supposed to be rather isotropic as far as the ground state is concerned. What is the success of this study is that we obtained various, by using different ligands, we obtained various contacts between high spin clusters through hydrogen bonds or through pi-pi stacking or through just van der Waals interactions like here in this case. In this case, this is the case of a perfect isolation with quite large distance between clusters. We have only one fast process, while in other situations where there is notable molecular contact, I mean, through the non-covalent interactions, we see two processes, one slow and one fast process. Okay, this I have shown you before. This was just a trial to induce the cooperativity and induce the spin crossover also on external side. So such a ligand is not the good point. Now we are working on further functionalization to observe better cooperativity and spin crossover on the whole cluster. Okay, these are some other approach. One of them is the opening of the cluster core. This was done after Professor Yu Song, who did it for copper tungsten. What we obtained in our case using trimetallic compositions is the enhanced exchange interaction, chiral space group, and impact of anion on the nuclearity. There is a clear impact for the 15 nuclears and 20 nuclears nuclearity for different anions. So this is the score for the whole chemistry of this cluster. To finish, of course, high spin molecules, so magnetic relaxation, chiral class and structures, using blocking and bridging ligands with different composition, we could obtain also these characteristics. We observed cluster structure opening, structural and geometrical isomerism, non-complete chelation, and what is the most important, and this is the biggest success of these studies, the trimetallic clusters with the tuning of properties. Yes, to conclude, we recognize the nanoscale molecular platforms for multi-component architectures, exchangeable composition and properties. Maybe in future we will be able to perform the structural expansion on the even larger coordination, even maybe through obtaining of the compositions with additional 4F metal ions. In fact, this is the big loss of mine. I'm very sorry of that. We also have the unique opportunity to study the spin crossover of single and simple, in parentheses, iron 2 isocyanide moiety in different coordination surroundings. So these are perspectives and challenges. We also plan with colleagues from Novosibirsk to study the high-frequency terahertz spectroscopic studies on similar, not this one, but similar magnetic manifolds. So these are kind of credits. Thank you for cooperation. The most of the things was done with Dr. Szymon Chorąży, who now leads his own project group at our in Kraków. For my PhD student Jędrzej Kobylarczyk and former PhD student Michał Liberka, and other colleagues from our faculty, from the Krakowian scientific community, and also from the external international institutes. So this is our new faculty. Please feel invited to come here, maybe to give some lecture, to see our new building and new facilities. Also, I would like to show you shortly some landscapes of Poland, going from the north to the south. These are my favorite ones, sorry. And also some greetings from Gliwice, a salt mine city where I moved about 3 years ago. So thank you very much for your attention. Sorry for taking 3 minutes more than I deserved.
Thank you. I think we still have time for a question, if somebody would like to ask. So I can see any, so perhaps I will start. Oh yeah, Artem, go ahead.
Hello, Robert. Thank you for a nice presentation. I have a question about solid solutions. When you replace some ions for maybe cobalt or manganese, did you try to introduce 3-valent 3D ions like to chromium? Is it possible in principle?
I did not consider this. I only considered the trimetallic compositions inside the cluster, but one can do this. With chromium, there is a problem of its inertness. So maybe you are not familiar with cyanide chemistry. Currently, there is no chromium tungsten or chromium molybdenum species with cyanido-bridges, probably because of the difficulty of combining chromium with cyanometalates. Yes, you can have Prussian blue analogs, but then the chromium is more as a hexacyanometalate. What I did try to do is to put some lanthanides. According to my approach, I was trying to use different types of ligand which are characterized by the nitrogen function to be coordinated cluster, and some oxygen function, not only this one, but also some other. Here you have the monooxides, but I only finished on some clusters with the coverage of this ligand. So this is still to be done if anyone would be interested in that.
Okay, thank you.
And maybe another problem is that probably the occurrence of this topology of this cluster is governed by the electroneutrality. You have always complex octacyanometallate -3 and 2D, two valent metal ions. I was not able to put something else into that. Probably. Yes.
Okay, thank you. There is also another question from Kira Vostrikova.
Hello, Robert.
Hello, Kira. Nice to see you.
Yes, it was very nice to hear you, to see your new directions. But I am synthesizer. For this reason, my question is devoted to the how it is difficult to control the content of your 2D ions from 1 to 9.
Yes, before we start to do anything else. Okay, knowing that, because we started from this composition, I think it was tungsten 6. Yes, this one. Iron 6, cobalt 3, and tungsten 6. So we started with that one. There was the first leading paper, and we have seen something which was quite new at that time. And now, before we do any other characterization and for these compounds, we perform the scanning microscopy measurements using EDS facility. So
no, excuse me, this is not the question how to control, but how organize the synthesis to obtain exactly exact composition.
You cannot, yes, I understand. I do not control the exact composition. What I do is I mix the metal ions in solutions just by calculating 1 to 8, 2 to 7 within the
by stoichiometry, yes.
By stoichiometry, okay. And then we measure the contents of each ion, of course, with some standard deviation of the technique. And then we draw the line like this, or the straight line, and judge how close is the composition in solid state against the composition in solution. So when we have a very nice line, we go into that. If not, okay, we skip some particular composition. In example, this one, I think, okay, this is on the borderline. This could be skipped. We could skip this. Yes, I hope I answered now the question.
Okay, thank you very much.
Okay, thank you. Thanks again, Robert. And we are to move further, and we are moving back to Moscow to Institute of Physical Chemistry and Electrochemistry. And our next speaker would be Alexander Martynov. Here you are. So the floor is yours.
Yes, so you can hear me?
Yes.
Great. Okay. So is it working?
Not yet, but it's, yeah, now it works.
Now it works, great. Just from the very last slide, sorry. Okay, so dear Chairman, thank you for a kind introduction, and the organizing committee, thank you for inviting me. Just like in 2018, I started my talk in Astrakhan at the MolMag conference, saying that we are newcomers in this field, and still I repeat the same words, we're still newcomers in the field of magnetic chemistry and molecular magnets. So there will be exactly one slide with the results of magnetic susceptibility measurements, but it would be more like an advertisement of what we can do in the field of lanthanide complexes with phthalocyaninates. So you know that in 2003, Natalia Shikava made an important breakthrough in the field of molecular magnetism by discovering the SMM properties of terbium-bis phthalocyanate. So this discovery actually contributed a lot to both fields, to fields of SMM and to the fields of phthalocyaninates. And in 2016, there was a review which covered about 70 examples of various molecular magnets based on namely terbium and dysprosium complexes with porphyrins and phthalocyaninates. So I'm pretty sure that this number will be doubled in the nearest future, and by the moment this area covered not only phthalocyanine chemistry, but also some other tetrapyral ligands, including porphyrins, porphyrazines, naphthalocyanines, and still there are a lot of other ligands to be tried. So modern approaches to molecular magnetism include for sure playing with substituents in the macrocyclic ligands, playing with the very nature of ligands, changing them from phthalocyanines to some other macrocycles, even playing with the very core of ligands, changing the heteroatoms from nitrogen, for example, to carbon, from carbon to oxygen and sulfur. Still, you can see that the values of barrier is not as high as, for example, those discovered by Layfield. But what is nice about tetrapyrolic sandwiches is that, first of all, they are relatively easy to synthesize. They are most of the time air and temperature stable, and moreover, they can be easily integrated into various materials and devices. So from this viewpoint, for sure, they are very worth of studies. While this approach mainly plays with the ligand field, another approach utilizes magnetic interactions between lanthanide ions and polynuclear complexes, which is mainly used to suppress quantum tunneling as a very fast and desired mechanism of magnetic relaxation. Making these complexes can include either synthesis of triple-decker complexes, which contain two metal ions. They can be the same metals, or it can be heteronuclear complexes, or different bridges can be incorporated into sandwich complexes to bind them into dimers or whatever. Another approach utilizes supramolecular chemistry. For example, recently there was reported a crystal structure of the heteroleptic mixed ligand double-decker complex, where terbium is sandwiched between phthalocyanine and naphthalocyanine ligand. So it represents very rare case of 1D polymer based on tetrapyrolic sandwiches on crystal, which provides it with a very high value of magnetic relaxation barrier. But as you all know, that crystallization is a tricky thing, and it is very difficult to predict, and it's maybe even harder to control the crystal packing of molecules. So we can use some other supramolecular approaches to form well-defined assemblies and species with collinear arrangement of lanthanide ions. For example, this example was also reported by Masahiro Yamashita recently. There was synthesized supramolecular. There was synthesized a double-decker complex containing crown ether substituents in one of phthalocyanine ligands, and in the presence of potassium ions, this complex formed supramolecular dimer, where terbium ions were in proximal positions. The distance between them was approximately 6.5 angstrom, which provided it with excellent magnetic characteristics. Our own long-lasting interest in crown phthalocyanines for sure was gained strong impact from the results reported by Yamashita, and we decided to contribute to SMM community with our complexes. We know how to synthesize various types of triple deckers containing different number and arrangement of crown substituted ligands, and we even know how to make controllable synthesis of heteronuclear complexes, where we can combine different combinations of diamagnetic and paramagnetic, or two different paramagnetic metal ions in well-defined positions. Recently, we succeeded to grow single crystals of a supramolecular dimer formed by this triple-decker complex containing one terminal crown-substituted ligand. Its dimerization was induced by addition of potassium tetraphenylbarate, and we got crystal structure of this aesthetically pleasant six-decker complex. You can see that we have different types of different distances between metal ions, ranging from 3.5 angstrom inside one of building blocks to nearest distances between different blocks. So for sure, these objects can be interesting. These molecules can be interesting objects for studies of long-distance magnetic interactions. But the problem with exactly this complex is that it's not very easy to separate it from reaction mixture, to separate it from other possible triple deckers which form in this reaction. And moreover, it turned out not to be as stable as we expected. During several months in aerobic atmosphere, it slowly decomposed with the formation of double decker and metal preligand. So to improve the stability of this complex, we decided to introduce electron donor substituents into the non-ionophoric phthalocyanine ligands, and we chose butoxy groups as these electron donating substituents. And thus we developed an approach to synthesize such triple decker complexes containing one terminal ground substituted ligand. It took us a lot to find optimal conditions to synthesize it, but finally the best conditions are written here. Is mixture of trichlorobenzene and octanol in the magic ratio of 9:1. Exactly in this mixture, it takes 8 minutes to reflux the reaction mixture to form this complex, and one simple chromatography to isolate it in a pure form. Moreover, this very rapid reaction rate allowed us to avoid any possible scrambling with formation of other combinations of Natalians and ligands, and thus we succeeded to synthesize series of homonuclear complexes, for example, containing 2 terbium ions in these positions, and heteronuclear complexes which contain either terbium or yttrium in different positions. Similarly to the previously studied complex, we found that it can form supramolecular dimers in the presence of potassium tetraphenylbarate, and we studied it by various physical chemical techniques, including, yes, so here we have the results measured recently by Dr. Nikolai Efimov from Kurnakov Institute, who showed that going from monomeric triple decker to dimeric 6-decker complex with 4 terbium ions has profound effect on growth of relaxation barrier. So by the moment, as far as I know, this value is the largest in complexes formed by binuclear triple decker phthalocyaninates. So these objects are also interesting from the viewpoint of studying of long-range molecular interactions. For example, we can use different heteronuclear complexes to obtain dimers with separation between terbium ions ranging from 6 to 13 angstrom. By the moment, we didn't start making magnetic measurements from these complexes, but we could use NMR spectroscopy to get first insights into their magnetic properties. And we can see that invariant to arrangement of terbium ions in these dimers, invariant to distances between these metal ions, we have very strong shifts of resonance signals of protons upon the formation of supramolecular dimers. So, for example, it means that we have influence from this terbium ion on proton located here, which are separated by more than 1 millimeter. For sure, it implies that terbium ions, even at very far, located very far away from each other, should also feel magnetic fields of each other, and these objects might be interesting for long-range interaction studies. These complexes can also provide some more information about influence of structural effects on magnetic properties. For example, we succeeded to get single crystals of this triple decker, and we saw that terbium ion, which is located in between ground substituted and butoxy substituted ligand, has square antiprismatic coordination polyhedron, nearly perfect. And terbium ion, which is located between butoxy substituted ligands, is in distorted state. So it's something between square prismatic and square antiprismatic. So we used NMR spectroscopy to get insight into the influence of these structural properties on magnetic on their magnetic behavior. This analysis was made due to the well-known equation which correlates lanthanide-induced shift observed in NMR spectrum, axial anisotropy of metal ion, and geometric parameter which is associated with polar coordinates of the considered proton with respect to metal center. So we made this analysis. We used X-ray structure for the assignment of NMR spectrum, and then we made the opposite direction studies. We used this NMR spectrum to extract axial anisotropy parameters, and we see that actually axial anisotropy in a distorted state here in for terbium between butoxy groups is by approximately 10% larger than in the case of metal ion located in the square antiprismatic arrangement. As far as we know, such increase of axial anisotropy can gain us several hundreds of K in terms of the relaxation barrier. Recently, we also studied complexes where can okay, so this example is actually example of, let's say, static control of the coordination polyhedron of metal ions, because we use ligands to form a certain coordination polyhedron and we don't change it afterwards. But recently we studied another class of heteroelectric triple deckers. These are sandwiches containing two neighboring crown substituted ligands. And we show that in its ground state, in its crystalline form, the crown substituted ligands are rotated with respect to each other, forming the square antiprismatic polyhedron of metal ion located between them. The same polyhedron is observed for metal ion located between crown substituted and unsubstituted. But when we add potassium ions, these crown substituted ligands actually adopt another conformation. They rotate with the formation of eclipsed state, and potassium ions intercalate between these crown ether groups, changing the coordination polyhedron of this metal ion from square antiprismatic to prismatic. On the other hand, another metal which doesn't participate in this switching remains in square antiprismatic state. So this molecule is a good object to study the influence of coordination polyhedron on magnetic complexes. With this aim, we performed NMR titration of two different heteronuclear complexes with switchable and non-switchable terbium ions with potassium acetate. So we used NMR spectra, and we saw that in the case when we observed switching, shifts of resonance signals of different protons were observed. But the same shifts of the, more or less the same order of magnitude were observed in the case of the complex where terbium didn't switch its coordination ion. Again, we used the powerful equation correlating lanthanide-induced shifts with axial anisotropy and geometry. So, since we had the crystal structures of both states of this complex, we could see that in spite of very strong rearrangement of molecules upon supramolecular interaction, actually the polar coordinates of protons. So here the black are normal state, white are states with potassium ions. They do not really change. So alteration of geometry is not enough to explain the observed shifts in NMR spectra. So we have to say that the only thing which is left is to explain it by increasing axial anisotropy. And indeed, we observed that switching of coordination polyhedron from square antiprismatic to square prismatic gets about 25% of increase of axial anisotropy. And in the case of complex where terbium ions do not switch, it also gets some increase, but it's relatively small, only by about 10%. So everybody who listens talks about sandwich complexes based on phthalocyaninates asks, is it possible to make something more than 3 decks or let's say 6 decks, which I showed previously? And The answer to this question is might be different. It depends on the structure of the receptor which we want to sample by interactions with alkali metal ions. For example, if we take a look at double-decker complexes, it is in some way similar to this sandwich, which has one terminal crown-substituted ligand. This molecule has two terminal crown-substituted ligands, and it seems that in the presence of potassium ions, it can undergo formation of 1D supramolecular polymer. But on the other hand, this molecule is also similar to another type of triple-decker complexes with two neighboring crown-substituted ligands, implying that in fact this complex also can undergo similar interaction with metal ions. So ions can intercalate between crown-substituted ligands. In fact, both types of interaction can be observed. Luckily, it is very simple to differentiate between them by spectrophotometric titration. And for example, in the case when intercalation of cations occurs between ligands, we observe batochromic shift in UV spectrum. And when formation of supramolecular polymers occurs, we observe hypsochromic shifts according to exciton model of chromophore interaction. If we take a look at structures of double and triple decker complexes, we can see that the distances between ligands in triple decker complexes are by quarter angstrom larger than in the case of double decker complexes because of bridging nature of the internal ligand, and thus metal bonds, the bonds from metal to this bridge are larger than from metal to terminal ligands. So we may think that in the case of triple-decker complexes, we observe intercalation, and we should observe the same intercalation in the case of double-decker complexes of the early lanthanides, which have the similar ligand-to-ligand distance. But in fact, it is more tricky, and the nature and the architecture of supramolecular aggregates formed by assemblies formed by double-decker complexes depends not only on the metal size of lanthanide, or the ionic size of lanthanide in the double-decker complex, but it also depends on the nucleophilicity of anion which comes with the potassium ion. And for example, for middle and late lanthanides with non-nucleophilic, relatively non-nucleophilic anions like icrate or tetraphenylbarate, we indeed observe formation of supramolecular fascial aggregates. And for nucleophilic anions with potassium salts with nucleophilic anions, we observe mainly intercalation type of interaction. But in fact, the same metal ion can form both types of supramolecular aggregates depending on the conditions, which is not a good result for our goal to study supramolecular 1D polymers. Thus, to overcome this intercalation, we designed new double-deckers. This work started recently, so there are not so many results by the moment, but I'd like to share them with you. So we know that intercalation occurs when molecules adopt eclipse conformations, and thus crown ether rings overlap, and potassium ions can fit into these positions. So what we decided to do is that we decided to extend one of ligands by addition of more rings, so that it cannot adopt, so that even in eclipsed conformation, crown ethers cannot overlap. With this goal, we decided to use two types of crown-substituted ligands. One of them is well-known crown phthalocyanine, and another one is crown-substituted oxyanthrene cyanine. This type of molecules recently came from our lab, and they showed numerous interesting photophysical properties. So you can see that the distances between centroids of opposite crown-substituted, between opposite crown ether rings are very large in the case of oxyanthrene cyanine, and they are much smaller in the case of common phthalocyanine. So no way they can overlap with the formation of sites for intercalation of potassium ions. So the third thing which we tried to do is to synthesize double-decker complex with crown phthalocyanine and unsubstituted crown oxyanthrene cyanine. Its interaction with alkali metal ions was studied by spectrophotometric situation, and here we show the results of its terbium complex interaction with potassium acetate. So we see that actually this process has two steps. Both of them are characterized by hypsochromic shift of the Q band in absorbance spectrum, which is characteristic for the formation of special aggregates. So we suppose that the first step of this process, formation of small discrete species like dimers, occurs, and then in the presence of excess of potassium ions, these small species combine together and the formation of 1D polymer occurs. So at the next step, we decided to use another type of oxyntranethionine containing additional butoxy groups in these positions of the macrocycle. These are the so-called non-peripheral positions of the macrocycle, and we know that they provide molecules with very interesting photophysics and increased basicity. So introducing these substituents, we expected that we can gain more diversity in switchable properties of these compounds. So at the first step, we decided to make a model double Jeffrey complex containing one non-uniphoric and substituted phthalocyanine and one butoxy substituted oxyntranethionine. Its interaction with potassium acetate was characterized by the expected hypsochromic shift of the Q band, which was typical for the formation of the dimer. So at this step, we understood that at least for formation of dimers, these butoxy units, these butoxy groups are not an obstacle. But the problem is that when we went to sandwich complexes containing both crown substituted phthalocyanines and butoxy substituted oxyntranethionines, we observed also two-step process upon its interaction with potassium ions. At one step, we observed the hypsochromic shift, and another step was photochromic shift. So this hypsochromic shift is highly likely to be attributed to formation of supramolecular dimers. But at the next step, we suppose that butoxy groups start to interfere with the supramolecular aggregation, and they prevent formation of 1D aggregates. But instead of that, formation of 3D supramolecular networks occurs with the formation of kind of G aggregates, following by this photochromic shift in the UV spectrum. So these results are relatively recent, maybe about 1 year old. We still have to confirm the architectures of these aggregates and study their magnetic properties, but we think that they're really worth the studies, although their synthesis is somewhat challenging. So to conclude, I should say that phthalocyanine chemistry is going through classical steps in modern science, going from synthetic step when molecules are designed and synthesized with different substituents, with different metal centers and additional functional groups. And at the second step, let's say post-synthetic level, their assembling and formation of hybrid materials occurs. So in the context of molecular magnetism, all these steps are very complementary, and I hope that you believe me that there is still a lot of things to be studied in phthalocyanine chemistry with respect to molecular magnetism. At the end, I would like to thank our group, our Laboratory of Novel Physical Chemical Properties in Institute of Physical Chemistry, and also group in Institute of General and Inorganic Chemistry, especially Dr. Nikolai Efimov for his help with the magnetic chemical studies. Thank you for your attention.
Thank you. We are slightly pressed on time, but I think we still can allow at least one question.
Yes.
So just for now, Sergey.
I see that there was a question in chat.
Thank you very much for so impressive presentation. Can you show us please slide number 11?
Yes.
Probably I didn't understand you when you told about interactions between terbium ions, did you also consider the interaction between neighboring molecules, from possible interaction, not only within one molecule, but between them? Or it was in solutions?
These studies, they were only in solution. These were NMR studies.
Thank you.
But it's actually a good question. For example, Yamashita studied similar extended sandwiches made by a slightly different approach, where the intermolecular distance between neighboring terbium ions was smaller than intramolecular. But it was only the intramolecular interaction which was responsible for improvement of SMM properties. So it's a good question.
Any more questions?
There is a question in the chat. So
we can see probably it's to you.
Yeah, so I think we can discuss it later. If I have time, I can answer.
You can answer, I think.
Yeah, so the question is that we are using this in why is it not working? Sorry. Yeah, that's an issue. So I was asked why we are using the base DBU in this case in the synthesis of double-decker complexes. This is something which comes from our experience in sandwiches, because in this DBU is needed to deprotonate metal-free ligand, which is used here, and in its presence, double-decker complexes are obtained.
Okay, I think we have to move further to the last talk of this session. Thanks you.
Thank you. Thank you.
And the last talk will be delivered by Natalia Gogoleva from Moscow Institute of General and Inorganic Chemistry. So, Alexander, could you stop transferring your presentation?
I wish. Yes.
And Natalia here.
What's going on? Yeah.
It's okay. It's okay. Now Natalia has to start her sharing. Okay.
Good afternoon, dear colleagues. First of all, I would like to thank the organizing committee for giving me such an opportunity to present our results here. As we know, interest to polynuclear complexes of paramagnetic metal ions connects with the importance of such compounds for understanding of exchange interactions between metal ions and potential use of such systems for magnetic materials creation. So, as well as wider use of polymetallic assemblies as starting compounds for synthesis of mixed oxide nanoparticles. As we know, carboxylates can transit strong exchange interactions between metal centers. There are some ways to change structures, features, and properties of synthesized complexes. We can vary metals, we can vary and combine ligands and their reactions. We can change synthesis conditions, and we can reorganize previously synthesized complexes. In our work, we use substituted malonic acid, and this it allows us to use the structure of complexes not only by variation of coordination types of ligands, but changing of substituent nature dramatically affect complexation processes and solubility of complexes. The aim of the study was to determine the influence of the structure of Trimetallic copper-lanthanide Malonates on their magnetic properties in the case of cyclopropane decarboxylase. It was found that reaction between copper acetate and tetrabutylammonium salt of cyclopropane decarboxylic acid with in the presence of lanthanide nitrate gave ionic lanthanide copper complex. Two bisphylate copper fragments crystallized with lanthanide octa-aquacation and tetrabutylammonium cation as counter ions. Copper is situated in tetragonal pyramidal environment with axial water molecular. Distances between all the metal centers are equal more than 4 angstroms, and metal atoms are not connected by bridging groups. When we added 18 crowns to the analogous reaction system, we yielded heterometallic complex, but structure experiment quality was very low, and we changed ligand to benzo-substituted crown to stabilize crown molecular in crystal. It appeared that complex had similar structure with a fragment of crown ester with a sodium atom as a counter ion in the place of tetrabutylammonium cation in the previous complex. The main elementary unit here, one of copper atoms coordinates one water molecule and another coordinates 2 water molecules and forms octahedral environment. When we used a barium salt of copper dicarboxylic acid, we were able to synthesize new 3 metallic complexes, copper, barium, and with combination of copper, barium, and carbon in it. All copper atoms are situated in octahedral environment with 2 water molecules, and barium atom coordinates oxygen atoms of crown ester molecule. Lanthanide atom coordinates 8 water molecules and shares 4 of them with barium. Previously, we have shown that copper can form a range of heterometallic complexes with barium and dimethylmalonic acid. Crown ester barium atom and made complexes much more soluble in organic solvents. In reaction of copper acetate with ammonium salt of cyclopropane dicarboxylic acid in the presence of lanthanide, we were able to synthesize polymer copper terbium cyclopropane dicarboxylate complex. Here, complex is built of bishalate copper fragment that connects with neighboring terbium atoms by means of carboxylic groups, 2 carboxylic groups of cyclopropane dicarboxylate anion. In crystal, there are separate fragments. Yeah, I present them. Copper coordinates 2 carboxylate atoms of 2 neighboring bishalate fragments of 2 neighboring polymer layers, and form 3D polymer framework was formed as a result. We were able to synthesize this polymer with a range of lanthanides, except erbium. It appeared that they were all isostructural. A similar structure motif in crystal packing was found in copper barium, cyclobutane dicarboxylate, and dimethyl malonates. Only metallic complexes were separated when we tried to add an donor ligand to the heterometallic system. And for the series synthesized copper-lanthanide complexes, investigations of magnetic susceptibility were carried out in a static mode in constant magnetic field. The values of Hete are constant up to 9 Kelvin and 20 Kelvin and 100 Kelvin for gadolinium, dysprosium, and terbium and dysprosium containing complexes. And then for terbium and gadolinium complexes, the values demonstrate sharp drop up to minimum value at 2 Kelvin. For dysprosium, Hete smoothly decreases with decreasing temperature. This appeared due to the presence of weak antiferromagnetic interactions between metal ions and in the combination of them an effect. The experimental values of Hetero at 300 Kelvin are satisfactory agreement with the theoretical values for isolated ions. In order to investigate the relaxation of magnetization of obtained copper lanthanide compounds and to understand whether they are single molecular magnets or not, we measured the magnetic susceptibility in the dynamic mode. The approximation of obtained frequency dependencies of the imaginary component of the dynamic magnetic susceptibility using generalized divide model made it possible to estimate relaxation times. The pre-exponential factor and value presented it, value of an energy barrier magnetization were determined. In order to make it into account the contributions of other relaxation mechanisms and for more accurate determination the values of energy barriers, experimental dependencies were approximated by in-hole temperature range using equations corresponding to sets of relaxation mechanism. And for the best data, the agreement between theoretical curves and experimental data were achieved by using Orbach and QTM relaxation processes for gadolinium containing complex and for Raman and direct mechanisms for dysprosium and gadolinium containing compounds. First, comparing the obtained values of barriers, it can be concluded that the best relaxation characteristics are possessed by copper dysprosium and copper terbium compounds with metal ions that are not linked to each other by bridging groups. For the standard coordination polymers, slow magnetic relaxation is completely absent, which can be explained by the presence of in this compound significant magnetic interaction between metal ions. The thermal decomposition of the trimetallic complexes was studied in argon atmosphere. It has been shown that tetrabutyl ammonium copper European complex begins to decompose already at room temperature. And the solvate water molecule is probably split off. The directed weight loss in the temperature range from 2 to 191 degrees corresponds to elimination of all 10 water molecules in complex. Further, at 215 degrees, the glass phase formation occurs accompanied by the weight loss that corresponds to the composition of organic fragments of the complex. Copper barium terbium complex with 18 crown 6 starts to decompose already at 53 degrees. Then there is one endothermic peak in DSC diagram that corresponds to loss of all water molecules here. And then the sample is stable up to 229 degrees when its organic part starts to decompose. At the initial stage of heating of copper gadolinium polymer, and the thermic effect took place, which is accompanied by decrease of mass, which likely corresponds to loss of occluded water. Then a complex series of complex effects took place, endothermic effects, and then it turns into exothermic effect with increase of temperature. This effect is accompanied with mass loss, and they can't be separated by this data, but we can assume that first effect is due to loss of water molecules in the complex. Most of cyclopropane decarboxylate complexes have the low stability between substituted Malonates analogs, but the synthesized copper-gadolinium cyclopropane decarboxylate demonstrate the highest thermal stability over 200 degrees. The possible reason is encapsulation of water molecules in the polymeric structure and stabilization of them by hydrogen bonds. So we can conclude that substituted malonic acids make it possible to synthesize a wide range of structure types of hetero-metallic copper-lanthanide complexes. The introduction of additional ligands can allow us to separate metal ions in complexes, or to degrade. They can lead to degradation of hetero-metallic core. Due to the use of crown esters, we can include to our structure one additional metal and synthesize 3 metal complexes. Then, from the point of view of obtaining single molecular magnets, the most promising are complexes with isolated metal centers. In our case, I would like to thank Russian Science Foundation for supporting our investigations, and my colleagues for collaboration, and you for your kind attention.
Thank you. Thank you. Now we have some time for questions. For now, yeah, Sergey, please.
Natalia, thank you very much for your presentation. So you showed the several structures which have such a porous features. So, for example, it was something like that. And as I understood also from your talk, they are quite stable at high temperature. Could we consider it as a candidate for probably chemical selective media using these porous dimensions? Do you plan to study them as such molecule active sorbents or something like that?
Thank you for your question. Yes, such studies were performed in the case of dimethyl malonates, but the porosity of these complexes is rather low, over 9%, not very high porosity. And concerning copper-lanthanide complex, these cycles are overlap each other, and there is no porous at all. So maybe yes, they can solve little molecules, but not very effectively. So.
Thank you.
Any more questions? I can't see any, so let's thank Natalia again, and also all the speakers of that session. And I guess we have like 10 minutes before poster session starts.